Today's lesson is going over our notes on stoichiometry and how you can convert from one chemical to another chemical using a balanced chemical formula and that molar relationship that they have. So this is going to require you to know how to balance equations. I'm not going to really pause the video to go through and show you how to balance. You yourself maybe might want to pause it so you can see if you can balance it for yourself and then check the answers as the video progresses. So we're starting off with the easiest of the options, which is a mole to mole conversion. Again, to do this, you're going to need the balanced chemical equation. So we have 2 to 1 to 2. We're being asked to convert 2.87 moles of oxygen into moles of hydrogen. So how many moles of hydrogen are needed if we want to completely react 2.87 moles of oxygen gas? So to do this, very easy step, we're going to be going from moles of oxygen to moles of hydrogen. And we're going to be using the coefficients that are in the balanced chemical equation to do so, because we know it's a 2 to 1 ratio based on that balanced equation. Moles of O2 are going to cross out, and our final answer here, 5.74 moles of H2. So this is kind of the foundational step in stoichiometry. You have to be able to convert from moles of one thing to moles of another thing. This should be in any of your stoichiometry problems somewhere, whether it be in the middle, beginning, end. You're going to need to use this molar relationship at some point, so this is really foundational. From here, we can convert mass to mass, because we can go from moles to mass of something by using the molar mass. Okay, it's going to be what we use here. So this is where you're adding things up from the periodic table, looking at the quantities within that particular formula. So we're going to balance this first, and what we see is this is a 1 to 2 to 1 to 1. And again, we don't have to put ones on those lines. It's implied that there's one there, so we don't have to worry about it. Question here, calculate the mass of zinc needed if 15 grams of hydrochloric acid are added to the reaction. So we need to figure out what zinc is required. So we're going to start off with 15.0 grams of hydrochloric acid. Let me put HCl there. And we're going to go from grams of HCl to moles of HCl. So using your periodic table, you're going to add up that hydrogen and that chlorine, and your overall molar mass should be 36.46 grams. So grams of HCl will cross out, and we're left with moles. Now we want to use our relationship, the molar relationship between HCl and our desired material, which is zinc, and we know that this reacts in a 1 to 2 ratio. Moles of HCl will cross out, and we're left with moles of zinc. We need to find the mass of zinc, so we're not quite done yet. We have one more step, which is going from moles of zinc into grams of zinc, and we don't need to add anything here. Just look at the periodic table, see what the value is. It's going to be 65.38 grams per mole. Moles of zinc is going to cross out, and we are left with 13.4 grams of zinc. Okay? Relatively easy. So let's go through a big example set where we have kind of 3 different questions here being asked, converting a lot of different things, whether it be moles to moles, grams to grams, or grams to moles in the case of C. So our balanced chemical equation, this is going to be a little bit longer. This is one that's good to practice if you need some practice balancing equations, because it does have some larger coefficients than our last 2 problems, a little bit trickier to balance. But the balanced formula is the following. So hopefully this is what you get if you tried to balance it yourself. So first one, A, is going to be the easiest, where we're just using a simple molar relationship between the oxygen that we're starting with and the Fe2O3 that we're ending with. So looking at your coefficients from your balanced chemical equation, we're going from moles of oxygen into moles of Fe2O3. So based off of our balanced chemical equation, this is a 2 to 11 ratio. Moles of O2 will cross out. I don't need to go any further. I'm done with the problem, essentially. And our answer here is going to be 0.01 moles of Fe2O3. Next, we're going to be going from grams to grams. So a few more steps. We're starting with our grams of Fe2O3, and if we're in grams, we need to get to moles. Moles has to be somewhere in this problem. So our first step is going to be using the molar mass of Fe2O3 to turn it into moles. So when you add up the 2 irons and the 3 oxygens, you're going to get a pretty heavy amount here, 159.69. your grams of Fe2O3 is going to cross out, and you're left with moles. At this point, you can use your mole ratio to get to your desired product because we have that balanced chemical equation. So this is going to be an 8:2 ratio. Moles of Fe2O3 will cross out, and our final step is going to be going from moles of SO2 into grams of SO2. So same thing, add up your sulfur, your two oxygens, which is 64.07 grams. This will cross out, and when you go and solve it in your calculator, the answer that you should get here is 12.7 grams. And then finally, we're starting with 16.1 grams of oxygen, and we're turning it into moles of SO2. So not quite as many steps as the one before, but not as few as A. So starting off with our given, which is 16.1 grams of O2. We're going to convert grams of O2 into moles of O2, and if we add up the two oxygens, it's going to be 32 grams. So grams will cross out. I'm now going to use my mole ratio to go from moles of O2 to moles of SO2. It's going to be an 8:11 ratio. Moles of O2 will cross out, and the answer that I'm left with is going to be 0.366 moles of SO2. Another example set, if you feel like you need some more practice, would be this problem here. So again, not a huge number of coefficients that you're going to need, not quite like the last one, but if you want to pause this and try to balance it, probably a good idea. But our coefficients are as follows. So here we're going to be using, like both of these questions are requiring us to use the most steps that we've seen so far, which is going from grams to moles, moles to moles, and then moles back to grams for what we're trying to figure out. So we're starting with 1.7 grams of iron, and we want to convert grams of iron into moles of iron. So taking a look at your periodic table, we see that 1 mole of iron is going to be 55.933 grams. From here, we're going to use our mole ratio to go from moles of iron into moles of iron oxide. This is going to be a 1:2 ratio. Moles of iron is going to cross out, and our next step is going to be going from the moles of iron oxide into grams of iron oxide. So this is a relatively large molar mass when you add up the two irons and the three oxygens, and you should get a total molar mass of 159.863 when you add all those up. Moles of iron oxide is going to cross out, and when you solve this in your calculator, the answer that you should get is 2.4 grams. B is going to ask us to start pretty similarly, where we're starting with grams of iron. So the beginning of our problem is going to look just the same, where we have grams of iron on the bottom, moles of iron on the top, and our molar mass on the bottom, okay? Now, however, we are trying to solve for grams of carbon monoxide. So we're using a different mole ratio here because we're going from moles of iron into moles of carbon monoxide. Our ratio here is 3:2. Those will cross out. And I need to get to grams of carbon monoxide, so I'm going to have to use the molar mass. Oops, crossed that out too early. But if you add up that carbon and that oxygen, it's going to be 28.01 grams per mole. And the answer that you should get when all is said and done is 1.3 grams of carbon monoxide. The next step in our process is using a newer conversion factor, one that you learned in Part A of the course, which is the quantity of a mole of gas at STP if you're looking at volume, which is going to be 22.4 liters. So provided you're at STP, that's the amount of space 1 mole of any gas is going to take up. So in this particular problem, we're going to be asked to go from mass of something into volume of something. So just like before, you're going to need the balanced chemical equation. Our coefficients are as followed. And we're being asked to find how many liters of, I don't know why the highlighter went on there, how many liters of hydrogen gas are going to be produced if we're reacting 23.92 grams of sodium. And notice it says we're at STP, so that means we can use that 22.4 liters of gas conversion factor. If we were not at STP, we couldn't use that, but we are. So 23.92 grams of sodium. first step we have to do, and remember, anytime we're doing stoichiometry, we have to be able to go to the mole ratio. So I can't work with grams. I have to turn it into moles first. So I'm going to go from grams of sodium into moles of sodium. This is going to be 1 mole, and on the periodic table tells us it's 22.990 grams per mole. This will cross out, and from here we can use our mole ratio to go from moles of sodium into moles of hydrogen gas. This is a 1:2 ratio per our balanced chemical equation. And if we stopped here, we'd be in moles of hydrogen gas. So your very last step is now going from moles of hydrogen gas to your desired unit, which is liters of hydrogen gas. So we don't need to worry about molar mass here. We just need to worry about our conversion factor that was always going to be the same if we're at STP, 22.4 liters per mole. So our final quantity is going to be equivalent to 11.65 liters of hydrogen gas. So here's an example problem, very similar to what we saw before, just different chemical formula. So our coefficients are as follows. And we're being asked to find the mass of potassium oxide if we want to produce 1.82 liters of oxygen gas. And again, we're at STP. So we're starting with 1.82 liters of oxygen gas, and we always have to get to moles, so we're going to be going from liters of O2 into moles of O2. So we're using our conversion factor for volume. It's always going to be the same at STP. And now that we have moles of O2, we can convert moles of O2 into moles of potassium oxide. This is going to be a 4:3 ratio. And now we can convert moles of potassium oxide into grams of potassium oxide. We just have to know the molar mass. So if you add up your potassium and your 2 oxygens, that quantity is going to be equal to 71.1 grams. When you plug this in your calculator, the answer that you should get is 7.70 grams of potassium oxide. And then finally, I think this is a little bit easier than before because you're, again, using that conversion factor, 22.4 liters per mole of any gas. So here we're being asked to find how many liters of hydrogen gas are needed if we want to produce 1.50 liters of NH3. And we're at STP. So we're going to start with our given quantity. Oh, and we need to balance this equation. Sorry. There are coefficients. So we're going to use our conversion factor from up here and go from liters to moles because we can't do stoichiometry if we're in any other unit that's not moles. So we have 1 mole, 22.4 liters. Liters is going to cross out, and we can go from moles of NH3 into moles of hydrogen gas. This is going to be a 3:2 ratio, and at this point, we just want to convert the moles of hydrogen gas back into liters of hydrogen gas, where we have 22.4 liters per 1 mole. Moles of H2 will cross out, and our final quantity is equal to 2.25 liters of hydrogen gas. And then we're going to have one more last problem. Again, just going liters to liters. In the case of A, it's liters to grams. But this is a little bit trickier to balance. Combustion problems can be a little bit harder to balance, so this might be a good one to practice on if you need a little bit of extra practice. But our coefficients here are as follows. So in A, we're being asked to convert 2.8 liters of oxygen gas, and we need to convert that into grams of water. So if you're in liters, you want to get to moles, you're going to have 22.4 liters per 1 mole. From here, we're going to go from moles of oxygen into our desired unit, which is water. So use your balanced chemical equation. It's going to be a 4:5 ratio. And now that we have moles of water, we want to get to grams of water because that's our desired unit. So going from moles to grams is going to be molar mass. So you add up your 2 hydrogens and your oxygen, which is 18.01 grams. Moles will cross out, and we get 1.8 grams of water. And then B, our last problem, is going to be going from liters to liters. sorry about that. So starting with the same thing, 2.8 liters of oxygen, same starting step. We're trying to go from liters into moles. And now we're going to be using our mole ratio to go to a different material. So we have O2 to CO2. This is going to be mole to mole. Looking at your equation, the ratio that you should get for these two is a 3 to 5. Moles are going to cross out. And then finally, we need to get to liters. So you're going to use that conversion factor that you can use when your gas is at STP, 22.4 liters per mole. Moles will cross out, and you are left with 1.7 liters of CO2. So hopefully this was a good review of the notes that we took in class. If you have any other questions, please reach out.